So I'm Andrew, and Evezor is our startup, and we're going to talk tonight about robotics. What do we want to use robotics for? For automation, to make your life comfortable, for entertainment. Programming robots is fun, but robotics is hard. And I don't know if you guys will like this or not, but I don't know if you guys have seen this video lately of Tesla's robot. You know, they try to say, oh yeah, you know, AI, we're going to do this. We'll have our robot fold some laundry. Well, it turns out that they actually had this thing just like as a puppet, and it wasn't actually doing anything but being a puppet. So robotics is hard. Why is it hard? So we'll kind of just like start from the very bottom and kind of build our way up here. With robotics, whatever programming languages you're using, you're probably going to have some kind of event loop where you're just going to go around and you're going to check stuff. And things that we're checking for, we can check things, and then we can have different kind of control schemes like on, off. You can think of that as like a furnace. So your air conditioning comes on when it's above a certain temperature. It will stay on until you get down to another temperature, and it will turn off. You have more high fidelity control schemes like a PID loop. It's just like on off, but it's a little bit more fine-tuned. You can also add in feed forward on that. Like say you have a vat of water, you want to keep this at a steady temperature. When you take some water out, some hot water, you will be refilling it with cold water, so your logic can kind of understand, I'm putting cold water in here, so I know that like I'm gonna have to go extra hard. I can hit on the gas pedal a little bit harder and get us back up to the temperature that we want faster. And so we have a few different type of control schemes: open loop, closed loop. You know, I'm controlling things. Do I know, say if it's a joint, whether or not the joint is actually at the position that you think it is, or if it's open loop and you kind of just like move over here and you don't really care to know where it's at. Moving on, I'm going to call these different kind of execution models. As you're doing robotics is difficult in the way that when you are running different types of code, your program is going to have to behave in different fashions. So you can have just raw code, in this case Python. You have your objects and your functions, and I'm not going to spend very much time here, but this is pretty easy to conceptualize for people, and you're kind of just running through code as you would kind of normal code. Then the next one up I'm calling command-based execution. And if anybody like has ever seen these things called whatever their names are, I've made these up because I've never actually seen anything out there that kind of explains things in the way that I'm trying to model these things. So the next one I call command-based execution, and this is something that you'd imagine seeing in a CNC machine. So G-code is kind of the fundamental programming language that was originated when these machines were first being made. And so you basically can break up this G1, X, Y, F move. Basically you have a function, which is G1, and then you have some keyword arguments after this. And a move command, like G1, will take a position and a velocity. So you can imagine that you have a robot and it's here, and you tell it that you want it to move over here. When you execute this command, it's going to take time for your machine to actually move to that point before you actually get to execute your next line of code. So you'll send this code, and whatever kind of fast-moving program you have actually like running the robot itself and not just this command execution model that's sort of like layered over the top, that has to sit there and hang and wait until this move command is done. But it's actually not even that simple either, because let's say you had that same line, but you broke it up into two pieces. So it's still a straight line. You don't want to move and then slow down and stop in the middle and then start up and go again. You want to be able to just like move straight through this point as if it didn't exist. So now you have to keep in mind that you're actually throwing more commands at your program than has actually happened yet. So you're actually kind of programming in the future. And this brings up some other problems if you want to do something real time. Like, what does this mean? Is it now, or is it the now and the future where you're actually executing this thing once the machine has got here, or before it goes in the planner, or these things just get a little bit muddled. Another type of execution model I'm calling just the frame or stream-based execution. And here you just like have a bit stream and you're just like spamming things out to buses or motors or whatever. I guess it's easier to talk a little bit about some of the encoding schemes. So you have DMX and MIDI, and some of these are ones that are used in the, what would I call this industry? In the entertainment industry. So, you know, you're a DJ or you're putting on a show. So with DMX, you periodically, in this case, probably a frame rate like you'd have in a movie or something, 20 on the order of 20 or 24 or something, you are sending out a bit stream that is the entire width of however many devices you have on there. So if you have 100 devices and they consume 100 bytes of information, every time you go through this, you will send out your 100 bytes. Whether or not, let's say it's something at address 1, you will have it and it's off this whole time. You'll just be sending zeros after zeros, just saying you're off, you're off, you're off, you're off. MIDI, on the other hand, is a little bit more elegant, I will call it. And with these, you have the same kind of information going out. In this case, you can imagine it like a piano. So with a piano, you have some key, and with this key, it also has some address value. So you hit the key, and you will get something that goes out onto the bus or into the MIDI transport layer that is what key was pressed and how hard you press the key. And then if you want to save these, oftentimes the MIDI format will be that you have the information of what key and how hard you pressed it, and then there'll be some kind of a delay timestamp frame that will tell you how long to wait until the next key was pressed. And so that's kind of how you encode MIDI. Music and movies and animations, these are all kind of in the same line. You know, you have an MP3, you're unpacking these bits. You unpack a few bits, you stuff them out, and you're kind of just like continuously sending bits out to have various things happen. Lights turn on, music to play, what have you. The last one is going to just be puppetry. And while this one isn't necessarily a standalone one, with puppetry, you'll have a bunch of sensors and a human in the loop. And as you're moving around sensors or pressing buttons or however it is that you have this wired up, your robot will attempt to follow these actions in real time. You can, let's say if it's a motor or something, you will probably have these coupled with the PID loops earlier so that you can nicely have your robot follow your motions. As you do this puppetry, you'll kind of understand it's like, well, yeah, okay, cool. Can I take some of these signals that are coming out through the human being in the loop, and can I put them into scripts and actually like start over at the beginning again now and kind of like program these things as different scripts and have them replay in different ways. So we are going to take a look here now at just a CNC machine. So why is it difficult to make these things go? And you'll see that there are a bunch of kind of steps that you have to go through that are very similar depending on the different types of actions that you're wishing to create. So here, pretty much for every CNC machine, whatever the shape of your machine, you're going to have some kind of motion platform that is going to move around whatever kind of tool or what have you that is going to complete your job. In this case, we are going to have a pen, and the pen is at the end of a robot arm. So we're also going to have the machine understand, okay, I have this pen out here, and in this case I have a servo. So how do we match up? What does this mean when some software is going to say, well, draw here and stop drawing here? How do we reconcile these differences and put this together? Kind of hand in hand, we are going to have the machine set up and this prepare artwork one, where, what is the toolpath that we're going to have our robot go in? We're trying to accomplish some job. In this case, we're just writing a bunch of cool text, and how do we tie these together? So tying them together is going to be this compiling script step here. So we have our machine set up, we have our artwork, and we're going to take yet another script, and we're going to put these together, and we're going to create something that the machine, the motion platform, can actually consume and run. In which case, we're doing that in the final little block here. Sorry, I guess I had this. I'm sorry?
Shout out to No Script.
Yes. Hopefully it brings me back where I was. Yeah, no kidding. Okay. Sorry about this. That seems happier. All right. So we have created some artwork. We have compiled it into a script, and I just have a short little 15-second thing going on here where it's going to draw it. And Inkscape does not care about order of operations, so take that for what it is. You can work a little harder to make it go in order, but it takes actual physical work, and I only had a couple days to make this. So again, let's do something else. In this case, we're going to assemble some circuit boards. So we have a similar kind of problem as we did with the first one. We have a motion platform, which is going to be a robotic arm. In this case also, we have more axes. We want to be able to take apart and move it in the z-axis, and we also want to be able to orient it to put it on a certain, orient it so that you can pick it up the way that you want to, and also place it down on a circuit board in the way that you want to as well. Again, just like the create artwork step, we are creating our circuit board. With our circuit board now, we are going to be able to export a file that says, I want all of these components at these locations, and you will get a what's called a board position file out. So that's going to have to be consumed later. We also have some other steps that we're going to have to do to set up our job. Our robot needs to know, okay, well, I have these parts that you want me to pick up. Where are they, and how do I ask a feeder or something for a new part? And where is the board? And there are all kinds of extra steps that we want to have when we're setting up a job like this, because we want to have more precision. So we also have a camera set up on this tool head, and in addition to all that, we need to say, okay, well, we have the suction cup here, and we have the camera here, and now our software also has to reconcile that when I see something with the camera here and I want to put it down there, like how do I change my shape of myself to accommodate the fact that like now I have a different tool head. And so all of that will be happened in this compile executable. So just like how we went from the artwork to something that will actually run, in this case we are going from a KiCad file and a bunch of our feeders locations, and we are going to compile that into another set of code. We're going to run that, and we're going to put together our circuit board. I will get a video of that eventually here. So how do we go about creating some of this? We're going to go back to the pen. It's like, I have this pen. How do we mesh together the fact that we have some generic code that's going to come out of Inkscape, and we're going to want to mate that with some other code that is going to raise and lower the pen when Inkscape does kind of whatever it thinks that you would want to do to make a pen plotter robot go. In all these cases too, G-code, while can be considered a standard, isn't standard at all. They all are different. We're having to, anytime that you take something from one program and kind of try to bring it into a different robot, you're always going to need to have some different kind of software that's going to suss that out. So anyways, we have the Evezor IDE, and it's a drag and drop programming environment. We're going to have some things like a checkbox that we can throw on the GUI to have this move our pen, and the servo is actually a PWM object out here. So let's go ahead, and I think that this is, sorry? I think that's where we were.
Yeah. It's black again. Wait a minute. What did you just do? He spoke.
I spoke? Yeah.
I probably thought so. I don't know where it was.
My microphone is green.
All right, it's back. All right. Go ahead.
Start again?
Yeah. Recording.
Yeah.
I'll talk to you about Thursday.
So I guess we are at the compile executable step. So in the compile executable step, we have all of our offsets that have been set in various places and various times. We have our board position file, which is going to tell us where we want all of our components. So we know where we want to pick stuff up from. We know where we want to put stuff down. And our compile executable will go ahead and just grab all of these requirements, put them together, and spit out a file that a robot will be able to do to actually run this code and put together our circuit board. So how do we get these software stacks and put them together? We have a million pieces everywhere, and we need to have something cohesive so that we can easily kind of understand where we can add functionality to a base level object and get the desired results that we want. So in this case, we have a few blocks here, and this is going to be what we're using to actually like set the pen up and down. So we have a checkbox here that is going to show up on a GUI, and as we set that, it will run through a little function block, and go to another GUI so we can see what the servo is doing. And then we have the actual servo object, which is down here as this PWM object with some extra variables that tell it what is up and down and whatnot. So we have all these pieces. So how are we putting together all of these pieces and having them act as a cohesive unit? This design pattern is called the actor model. And in this, you have an actor that's a basic building block. And as you're wiring them together, each actor itself has its own internal state and its own way of handling messages when they come in. So the only way to communicate from actor to actor or with an actor should be through messages. So you can kind of think as all of this, it's each actor is a little bit of code and it's wrapped in an API. And so when it gets a message, it will decide itself on whether or not it wants to go and check some hardware, or if it wants to do nothing or send messages to other actors or create actors. There is a myriad of different ways, but having this actor model also gives you the benefit of being able to communicate across different communication schemes, be it CAN bus or MQTT or any of these. Because everything is all message based, you can sort of divide up the divide up your computational load or your hardwares in different places and have them work as a cohesive whole. I guess that's kind of the end of my slides here, and then I was going to pull up some of this. So this is actually connected to a robot on the table there. If you remember, how about I open up, I can go ahead and just open up this entire program here. So you will remember that we had the pen and this here. So we have this checkbox called set pen. And when we come over here, you can see that this set pen checkbox has automatically been added because we had it in the program. And you won't be able to see it on the camera here, but as I'm pressing this set pen, you will see that when I press it, this pen position slider, which also is here. So this checkbox is going to send out a message to this function block. This function block is going to say, oh, if I got a true, I'm going to return 0. If not, I'm going to return 1.
Can you zoom in on that, make the font bigger? Yeah.
So when this code block gets a message, it's going to say, you know, is this event true? If it's true, it's going to return a 0. If not, it's going to return a 1. That's going to go to this GUI slider. And then the slider is going to send a message to the servo itself. So you can see here, when I do this again, you'll see that as I check this, this pen position slider is actually going to move. And you can also go, and I know you won't be able to see this on the video, but as you go and move this around, the servo is actually moving between its lower and upper bounds. And there are a bunch of other objects that have been put up here based on the objects that have been in our program over here. I'm just going to quickly go through a couple of these, I guess. What's another fun one? We have some of these compilation steps. So we'll go ahead and look at the pick and place one. So with this pick and place, we're going to have our feeders here, and they're going to have some informations. We're going to have an offset. Now, again, when you had this on a bigger machine, some of these objects will actually be asking the machine instead of just some dictionary object. But anyways, we have a, this is the position file that will come out. So let's go ahead and we will run this. So let's open this in a new tab. Sorry?
Keep going.
So because we have some 3D objects in our on our canvas, it's going to automatically populate this. We have this automatically populated. We'll go ahead and just run this guy. So it's sending the messages. We have the CSV input. So this is going to be that first block. We're going to go through KiCad, and it's going to generate some toolpaths. We are going to take that toolpath. We're going to put it into another 3D viewer. We're going to take the output from that one, do some kinematic transforms on it, and send that to another viewer. And so you can see here, we have our CSV file. We have our KiCad output. So that's going to be, how about we give us some colors here. So the KiCad output is going to be this kind of purpley color. And then if we're going to want to run this on a robot arm, now we're going to actually have to change the kinematics so that we are running with positions of the arm instead of XY coordinates. And that is going to be this last one here. Again, a bunch of these things have, we have this P&P feeder GUI element. So this guy is going to actually go ahead and throw this up here. So when you're actually using a robot, you can say, hey, robot, like, where am I right now? And I have these components here so that we can reconcile what component is where. And when we pick them up out of these CSV files, the robot's going to know how to move what and where. Are there any other fun ones? Here's just how we did the pen drawing. Actually, let's see if I can. Sorry, computer's dying a little bit here. Oh, am I going the wrong way? So just like the pick and place, we kind of have the same kind of operations here. We are having our raw file come in. We're going to deconstruct what the Inkscape is going to put out. So let's go ahead and just run this real quick, and then we'll close this up. So again, we have our input and our output, and we can also transform our drawing around. So you don't necessarily have to set something up in Inkscape to know where you want it with the machine. You can take this intermediate format and move it around. But yeah, so robots, they're hard. We'll make it easier.